Welcome to a new series of Coonrod's Corner videos, the real world of RF printed circuit boards. Today's topic, how does long-term exposure to elevated temperatures affect microwave and millimeter wave performance? Now here's your host, John Coonrod.
Hello, my name is John Coonrod with Rogers Corporation. I am a technical marketing manager. Today I'm going to be talking about how high temperature exposure over long periods of time can affect a circuit operating at microwave and millimeter wave frequencies. Now this is a pretty big topic, and I really can't get into a lot of detail in the video here. However, you can get a lot more detail if you're interested by going to our Rogers Technology Support Hub and there search on the topic that I'm presenting today, or also some of the subjects related to it. And also you have the ability to contact an engineer in your area from the Technology Support Hub. So with that, let's go ahead and get started. First off, I'd like to say there's two general categories for materials that are used in the high frequency industry. There's thermoplastic and thermoset. And there's a lot of different ways to think about them, but essentially a thermoplastic material can reflow. Once you get to high enough temperature, it can actually melt and come to a gel state, so to speak. And then you can cool it off and it solidifies again, and then you can go back up in temperature and it will melt again. However, our thermoset material does not do that. It's basically a cross-linked system that is locked in place, and as you heat it up, it can soften some, but normally if you heat it up, it will not melt. If you heat it up enough, it could actually decompose, but anyway, that's the big difference. The thermoset is more rigid, it's more locked in place, you might think of, and then the thermoplastic's softer. And the two different materials behave a lot different for long-term thermal exposure. Most of the thermoplastic materials used in our industry, the high-frequency printed circuit board industry, most of those thermoplastic materials are PTFE based, and PTFE materials do not oxidize at these high temperatures or any temperatures. However, thermoset materials, they do oxidize, and over some period of time you can have oxides build up at the surface, and then the oxides at the surface can actually change the dielectric constant or the dissipation factor of the material. So here is shown a testing that we did for exposure to high temperatures over a long period of time. X-axis is time in hours, and just for a reference, 1,000 hours is about 42 days. And here we're testing the 31 mil thick RT Duroid 5880 substrate. And you can see that we're testing at different temperatures, 100 degrees C, 150, 200 degrees C. Now 100 degrees C is not that uncommon for operating temperatures. 150 C, that's a little more aggressive, and 200 degrees C is considered very aggressive. But what you can see here is that the dielectric constant really doesn't change that much. As a percentage, it's less than 1%. And that's true with a lot of materials that are thermoplastic, that they will not oxidize, and they really don't change performance over long periods of time at elevated temperatures. The chart shown here is also thermal aging studies that we've done. In this case is accelerated aging, and the x-axis is much farther out in time, and just as a reference, 1 times 10 to the 5 in hours is about 11.4 years, so this is really long term. And what we're showing is the difference between thermoset materials that are aging at just room temperature, 25 degrees C. And the blue dots, that's our Rogers RO4835 material, which has the same electrical performance as the RO4350B materials. However, the RO4835 material has improved thermal aging characteristics, basically 10x. So it will still come to the same oxidation level and shift in dielectric constant, but it takes 10 times as long as compared to the RO4350B laminate, which, by the way, the RO4350B laminate's been used for decades in high temperature applications and works quite well. So the 4835 is just one step beyond that. You might say it's optimized for these higher temperature exposures. The data shown on the previous charts is really test the material for exposure to these elevated temperatures, and it's actually a material test. So what we do is after we make the laminate, we etch all the copper off and we expose the substrate to these different conditions, and we test it periodically. And that's not exactly what happens in circuit form, of course. And in circuit form, there are copper traces, and the copper traces actually protect the substrate below it from oxidizing. So you get a different response in circuit form. And the information that we share very often is the raw material itself being tested, and that's really a worst case scenario. And I'm going to show a few more charts that shows the difference between testing the raw material and also testing in circuit form. The illustrations shown here are showing differences between a microstrip circuit on the left and grounded coplanar on the right, or Also microstrip edge coupled feature that I've have it labeled as. They both have a similar property when it comes to how electric fields fringe like that and couple. So anyway, on the left, you can see that a microstrip circuit is simply a signal conductor on top, ground plane on the bottom. And if you go through, let's say, a mild exposure to elevated temperatures for maybe a few months, you'll get some oxidation at the surface, and you can lightly see that on the left side and the right side of the substrate surface, right and left of the signal conductor. And it's a little bit of yellow area, and if you look closely, some of that yellow area will go underneath the conductor a little bit, and that yellow area represents the oxidation. Now, if you do a more aggressive test, either longer in time or higher temperature or both, then the bottom left picture of the microstrip circuit is showing increased oxidation, and that is going to change the dielectric constant at the surface. However, for microstrip, and I didn't show the fields there, but as you probably understand, microstrip has a lot of fields between the signal plane and the ground plane at the bottom, and most of those fields are going to be protected from the oxidation, so the microstrip will not respond to oxidation as much as it would if it was in the raw material state. And then to the right is a microstrip edge coupled maybe it's a segment of a filter. And what I'm showing there is that you do have some fields in odd mode where they are using the surface of the material between the two conductors. And when it's lightly thermally aged, then you get less oxidation, more thermal aging, more oxidation. Now these fields that are coupled there, they are going to be affected by the oxidation. So anything that is coupled, whether it's edge coupled filter or a grounded coplanar waveguide, whatever it may be, if it's coupled, then the oxidation effects will impact that structure more than a structure like on the upper left, the microstrip that's just a single-ended transmission line. Now there is a diffusion limit to this. In other words, once you get enough oxides built up at the surface, they will just no longer accept more oxides. So these oxides will not actually migrate all the way through the material. It's usually just a surface effect only. The graphic shown here is another accelerated aging test that we have done, and in this case what we're doing is comparing transmission line circuits to the raw material test that I described that is testing the exposed sample. So basically the sample in a fully etched test, basically the entire sample is being oxidized. However, in circuit form, as we've showed on the last slide, you can see that the oxides are just left and right of the signal conductor. You get some fringing fields there, and it's much less of an effect. Now in this case what we're showing is the difference between the 20 mil thick Rogers RO4350B laminate and then also the 20.7 mil thick RO4350B low pro laminate. The big difference between those two laminates is the copper surface roughness, where the standard has relatively rough copper and the low pro has low profile or smoother copper. Now you can see that the yellow dots, that's the fully etched samples that were exposed entirely to the conditioning and also had oxides build up all around it. And then the other dots are also testing at different temperatures, as you can see, but they're also microstrip transmission lines, and you can see that the transmission lines do not respond the way that the fully etched circuits do. And when we offer information on oxidation and aging, a lot of times we'll give you the information with the yellow dots and realize that's very conservative, and in reality you probably should talk to us in a little more detail to understand how the circuit could be impacted by the oxides. And in this case you can see transmission lines are not affected by the oxides near as much as the test we do, which is a test on the full substrate itself. In the graphic that we're looking at now, we're doing comparisons with circuits and, again, the fully etched samples being the black curve, and then the circuits are transmission line circuits and also edge-coupled filtered circuits. So you can see that the transmission line circuits, the solid red and solid blue curves, are less impacted than the edge-coupled filter circuits, which are the dashed red and dashed blue. And then the one that is affected most in this graphic is the black curve, and that's the fully etched samples that the entire surface has been exposed to the oxides. In summary, thermal aging can affect the circuit in multiple different ways, and the thermoplastic materials are less affected than thermoset materials. And in the category of thermoset materials, it depends on the formulation. Some thermoset materials will age better than others, and the aging really comes down to oxides building up at the surface. Now, if the RF designer understands this well, then they can account for that for long-term exposure to elevated temperatures, and that does need to be accounted for in terms of simulations and really trying to understand long-term reliability effects. This concludes this session of Coonrod's Corner. Thank you for watching.
For additional information and technical tools, if you're not already a member, join the Rogers Technical Support Hub and gain access to calculators, technical papers, and more Rogers Corporation informational videos. Rogers Technical Information is also available at your fingertips with the Rog mobile app, available for the iPhone, iPad, and Android devices. Check it out today.